grade it.
Well,
But
that means I can't raise my percent, so I'm
Well,
stuck at 50%.
okay, well, keep hold that thought. You're in the right. You're going the right direction. So this one actually finally talks about some things we talk about if you see a compound and it's represented one way or another way, what is it really representing? And we'll also talk about functional groups. So we have the Lewis structure, which you're familiar with. The pot of valence electrons has to be distributed. There's Mike. And then we have Kukulay structure and structural formula, and I'll kind of show you what they look like. Kukulay structure, no electron pairs, and structural formula, in general, they get more and more vague as you go down. So structural formula is kind of even less. So I'll show you some examples. Semi-structural formula, condensed structural formula, and line formula. Now on the test, I don't ask you which is which, okay, but I'm just going to kind of talk you through some examples, okay. Line formula is the least, line formula, you have to use your most amount of imagination. So here we go. Oh, before I get there, in Chem 1, we talked about the molecular formula and empirical formula. Okay, so I kind of usually say a molecular formula is the real deal, and empirical formula is reduced from the molecular formula. So let's see if you guys remember how this goes. So the formula for benzene is C6H6. Okay, that's the molecular formula. What is the empirical formula? CH, exactly. Okay, so that's the reduced version. So that's all we mean by that. So again, it's easier to show you what all those different formulas mean rather than to kind of say blah, blah, blah. Okay, so aside from the Lewis structure, now we're on to the Kukulay structure. Okay, it doesn't necessarily, I think your description said for this type of structure, it doesn't show you lone pair electrons. I'm fine with that, okay. So that is what, that's a hydrocarbon, right? 4-carbon hydrocarbon. It's what we call an alkane, all single bonds. We're going to be talking more about that today. So this is the same, actually down here is the same structure, okay. These are both 4-carbon alkanes. And they all are kind of having the what we call the carbon chain, straight hot dog sort of thing. Carbon, 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 carbon in a straight line. Okay? Now, we've been talking about this, how if you see, for instance, a carbon with 3 hydrogens, you have to interpret it as that. Okay? You see a carbon with 2 hydrogens, you have to interpret it as that. So, yeah. And then here, it's kind of even more condensed, where basically they're basically saying, well, look, you got 2 of these, so we're going to show 2 of those with just kind of quantity, CH2 quantity 2. Okay. A structural formula. They get even less descriptive. This is a line formula. Like, really? So at the ends and at the vertices of the segments, you put carbons. So if you wanted to kind of unpack this, I would put a carbon here at the end, carbon at the vertice, carbon at the that vertice, carbon at that end. Okay?
Are they just assuming all the hydrogens
Yep.
are in place?
Yep, and so this sort of simple line structure assumes that, well, let's see, how do I say this? You guys remember the expected valence, like how many times it's going to reach out? And that is sigma and pi bonds. So it's going to reach out, and you do, is it 8 minus the group number? So carbon is group number 4, so 8 minus 4 is 4. So this goes back to you. If this is reaching out once there for that carbon, then by golly, you better fill the rest out for this particular line formula with hydrogens. Okay, so H, yep, H, H. And then this guy right here, this carbon, is reaching out 1 for that carbon, 1 for that carbon. It's going to reach out 4 times. Those are both single bonds. It needs 2 more single bonds. So that's why we go hydrogen, hydrogen. Okay? So we can kind of reconstruct that line formula. We'll match those others. All right. Semi-structural formula. Let's see how many carbons we got here. 1, 2, 3, 4, 5, 6. I count 6 carbons for 2 reasons. One is to kind of get a sense for what the structure is. And when you go to name this thing, which we're going to kind of dabble with naming these things, you basically take the longest carbon chain, and that's going to be your root name. So it'd be some sort of hexane. Now, in this case, do you see, though, that this carbon, well, both carbons, this carbon has, and I'll go ahead and if you want to write in your notes, you can. You've heard me use the word methyl before. CH3 is a methyl group. Methyl, not ethyl. Okay? Anytime you see, oops, sorry, there you go, final answer, methyl. Okay, so in this case, we have the carbon that is, we could unpack this and have a carbon that is actually, that last carbon is singly bonded to two methyl groups. So I'm going to kind of unpack this up here. So do you see where kind of the more detailed structure is above and the less detailed structure is below? So, for instance, this right here, when I said, oh, I said 3, I said 2. Oops, sorry. I got 2 over here. It's been too long. Sorry, organic chemistry, it's been far too long. Okay. So this 3 right here means that that carbon has a methyl group, and a methyl group, just like it's shown up here. Okay? Methyl, methyl, methyl. And this 2 right here means that this carbon actually has 2 methyl groups. Now remember I said it needs to connect to 4 things. So do you see where this carbon is singly bonded to this carbon, singly bonded to this carbon, singly bonded to this carbon, and the last thing is a hydrogen. So it's got 4 things. All right, back to the Kukulay structure. Now this is not a hydrocarbon. There are a lot of cases where, and we did this when we did a combustion analysis, there are a lot of times when you have a compound with carbon, hydrogen, and oxygen. Okay, so this actually has what we call, well, I guess it's not 2 functional groups, separate functional groups. Let's see, how many carbons in this root though? 3, I agree. Okay. Notice the Kukulay structure kind of blows off the lone pair electrons. If I was guessing, I'd probably put lone pair electrons kind of here-ish, just guessing. Okay, and probably here-ish. That's the Lewis structure. That's not my point, though. What is my point? So this case, we're kind of taking the hydrogens and kind of balling them up with the carbon that they're in. So the first group, of course, that CH3 stands for, this is balled up here. Okay, this CH2 is right here. Okay, and then actually it looks like what we need to do is still maintain this structure right here. So it's the same thing. Ooh, line formula. So the line formulas, at the ends, we do a carbon. Okay, so I put carbon here, I put carbon here, and then also carbons at the vertices. And again, it kind of hurts my brain, but it's been a long time since I've dealt with these. But we're back to our 4, oops, no, I did that wrong. Okay, yep, that's what I said, it's been a long time. There, final answer. This end actually of the line was taken up by oxygen. It's not a carbon. Sorry about that. So now we're back to the same. For instance, this is this. Final answer.
So you write it that way because that double bonded oxygen doesn't connect with the OH at all?
Right.
Otherwise it'd be like CO-OH.
This double bond oxygen only connects with this carbon.
Yeah, so.
Right. Yep. And this is actually called a, I'll go ahead and put it here. Here it might be something else because we have it next to a carbon with a double bond oxygen, but OH is a hydroxyl group. Hydroxyl. Now the cool thing about hydroxyl groups, guess what? What's so cool about hydroxyl groups in types of intermolecular bonds?
Hydrogen bonds?
Yes, hydrogen bonds. Hydrogen bonded to an oxygen, nitrogen, or fluorine gives you kind of that very polar sort of thing going on.
I thought OHs were alcohol.
They are. They're also hydroxyl groups. Alcohol's more generic than hydroxyl. So all alcohols have a hydroxyl group on them. So that's kind of how I would think of it. So clear back at the beginning, we talked about this idea of bond polarity. And just to kind of revisit that, I was looking at my notes, I'm like, oh, we've already talked about this. But I kind of said anytime you see a hydrocarbon, which is carbon and hydrogen in them, just kind of think of those bonds as not being polar enough to make it a polar molecule. So basically, they're nonpolar. And here's where I want to actually kind of break out and talk about the different types of hydrocarbons. There are alkanes, all single bonds. There are alkenes, it has one double bond. And there are alkynes, it has one triple bond. So I guess just for kicks, I'll put a dash over alkanes, a double dash over alkenes, and a triple dash over alkynes. This is a quick and dirty kind of look at this. Benzenes. We talked about the benzene ring. Has 6 carbons. And remember, this is the one where you have to do alternating single, alternating double. Alternatively, you do the hexagon. Oh my goodness, that's ugly looking hexagon. And you do a circle in there to kind of show that. Benzene. Alkyl benzenes, they've got substitutions of methyl groups or alkanes on the benzene ring. But basically think of them as nonpolar. Okay, so alkanes, just a single dash, everything is carbon and hydrogen, everything is singly bonded. The simplest is 1 carbon, that's methane. Okay. We go from 1 carbon here on the slide to 4 carbons. Anytime in organic chemistry you see the prefix BUT, that's bute, think 4. Okay. And alkanes end with ANE, so that's kind of nice. So it's butane, butane, I guess. I don't know where the meth came from. Methyl group is the CH3 group, but. So now this one down here, and again, this is just quick and dirty. This is just quick and dirty. It's been so long, I hope I don't totally butcher this up. But what you do when you're presented with a structure and you're supposed to name it, is you go with whatever is the longest carbon chain. So I could go 1, 2, 3, 4, 5, 6. I'm like, no, if I do a turn there, I'll get more. 1, 2, 3, 4, 5, 6. Notice, no. And actually down here, if I go 1, 2, 3, 4, 5, that's not the longest. So 6 is the longest, and actually I'm going to name it the same whether I go with the red or the green. So 6 is the longest. They're all single bonds. So it's going to be an alkane. 6 is hex, so that's why we get hexane. And then we need to go ahead and say, what else besides hexane do you have? And I'll go ahead and take this red and circle my hexane. Well, I've got a methyl group here and a methyl group there. Okay. Then what you do is start from the side where you get the lowest number. Like if I called this carbon 1, carbon 2, carbon 3, carbon 4, so I had 4 methyl, carbon 5, 4, 5 methyl. Okay. I don't want to do that because 4 or 5 is bigger than this way. Okay, 1, 2, 3, 4, 5, 6. And if I do it that way, so I call this 1, 2, 3, etc. Then there's where I get my 2, 3, and here finally, naming organic compounds, finally, you get to use the di prefix for 2. So 2, 3 dimethyl hexane is kind of how that goes. So again, there's more to it, but double bond, an alkene, okay? If it's just 1 double bond, 2 double bonds, okay? So notice that we still have carbon that has bonded to 4 things. So let's make sure, or bonded 4 times. So this carbon, okay, notice that it's got hydrogen, hydrogen, and then it's got a sigma bond to the carbon and a pi bond to the carbon. There's your 4. Okay. If we go out here, 4 things, hydrogen, 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 single bonded to a carbon. So we use the prefix PRO for 3, okay, and ENE for an alkene. So propene is what this is. Now, beyond propene, we have to say where the double bond is, and that's why this is the way it is. If I start counting carbons, the most carbons I can get is 4, regardless of where I take my turn up there. So it's a 4-carbon alkene. So, 5. 5. 1, 2, 3, 4, 5. Okay, so it's a 5-carbon alkene. That makes it pentene. So we kind of start from the back and move forward. Okay. So branching, 2 things about that pentene. We need to say what carbon the double bond occurs on. And if I go with carbon 1, 2, 3, 4, 5, okay, my branching is on 2, thus the 2-pentene, and I have not the branching, I'm sorry, the double bond is on 2, and my branching is also on 2. Now, could the methyl group been on something else? Yeah. Would it have different physical properties? Yeah. Isn't that so cool? I mean, you just move the methyl group around and you have different things happening. You move where the location of the double bond. In organic chemistry, they actually then talk about how you kind of get what you want, how you synthesize things to put the double bond where you want it and substitution where you want it. So double bond hydrocarbon, so it must be some sort of alkene. Notice that now in this case, the most number of carbons I can get is 4. Now this is kind of showing you kind of a bend in it. So I can call this, it doesn't really matter, it's symmetrical, isn't it? 1, 2, 3, 4, okay? In this case, there's no methyl groups, no nothing, okay? But notice, and we'll talk more about this has been a while. Let's see, cis, trans, yeah, okay. I think of a cheerleader, okay? There are 2 ways that those kind of, the carbons can kind of branch off. The reason is that there is not free rotation around that double bond. I don't know if you kind of remember pi electrons, but it's stuck. So there's an orientation issue, okay? In this case, this is the trans, okay? We have trans, and then we have cis, okay? Trans means it's catty-cornered, okay? Cis means it's actually on the same side of the double bond, okay? So this would be cis, this is trans, okay? So, and yeah, I guess you do need to say where the double bond is. The double bond's after the second carbon, and it's in a trans configuration instead of a cis. That's about the extent of everything I remember. Here's benzene, go ahead.
Will we need to be able to name them or just recognize them?
Just recognize them. Yeah, I'm just kind of adding the naming, just kind of
Okay.
and butchering it a little bit. Not too bad. Okay. So there's our cute little C6H6, which you guys told me the empirical formula is CH. Okay. So this kind of goes back to a line structure where at each of these vertices you picture a carbon, and then also at each one of those vertices you picture a single hydrogen. Yep. So benzene is a very reactive molecule. And so we can do substitutions with those hydrogens. So one substitution is to take the hydrogen off and put a methyl group there. And that's called toluene. Okay, this is actually this hurts my brain. This is actually 2 benzene rings stuck together, naphthalene. This is the stuff in mothballs. It makes it smell kind of spicy.
In what though?
Mothballs?
Oh,
You put in
okay.
your closet?
Yeah.
Yeah. Okay. So those were all, well, they weren't all hydrocarbons. Okay. But if you take a hydrocarbon and add oxygen, you have taken, hydrocarbons are nonpolar. When you add oxygen, yeah, you might get a little bit of polarity, okay, to the molecule. So I'm going to kind of talk you through. First off, your oxygen. If your oxygen in like an alcohol or a hydroxyl group, if your oxygen is bonded to a hydrogen, you have hydrogen bonding going on at that part of the molecule. Now the problem comes in, and we're going to look at this as an example, is if you have your kind of, their polar end. If you have like a lot of carbons after this, carbons and hydrogens, carbons and hydrogens, carbon and hydrogen, basically you have a polar end and a non-polar end. And this is kind of what we were talking about with detergents. Okay. If you have an oxygen and it's not bonded to a hydrogen, then your pure substance cannot hydrogen bond. That makes sense. So I like, I've done this for a long time. Too long, no. This actually has my maiden name up in the corner. Of course, my name is Elizabeth Snipes, and it used to be Newton. So you know how old this is. This is from the front cover of my organic book that I used way back when at the University of Northern Iowa. So from me to you. Okay. So I thought I'll kind of show you, how you read this. On this thing, anytime you see an R, that just means R is anything. Okay. So for instance, if we find alcohols, not so surprising. This is alphabetical. Yeah, good. If you find alcohols on here, you find R, and you would probably do OH. So that's how we kind of do this. So R is generic dash OH. Hydrogen bonding with alcohols? Yeah. What is R? It depends on what your alcohol is. Phenols were P's. This is just so helpful. I tried to, and I did find this kind of on the internet, and I haven't found anything I like as concise as this. It's funny, you go back to what you know. Phenols now, you see AR. AR is an aromatic ring. So I'm going to go ahead and I'm going to draw my benzene ring. Circle for showing kind of the alternating single, double. And anyway, in resonance. And I'm going to do OH. Okay? We called that what toluene before, didn't we? But any kind of generically sort of thing you have going on, that is a phenol. Let's see, what else do I have? Carboxylic acids. C. Carboxylic acids. Oh, there we go. This other one, I'm going to go with the first column. R-C, double bond O, single bond OH. Okay, we actually saw one of those a minute ago. Carboxylic acids. What's the R? I don't know, some sort of carbon and hydrogen. But the functional group we're focusing on is carbon, double bond oxygen, single bond hydroxyl group. Okay, these are all things that can hydrogen bond. Yes?
So the R's will always be some carbon and hydrogen.
Yeah,
combination.
yeah. It can be some I guess it could really be, your R could also be carbons with other functional groups. You know what I mean? It doesn't have, you could have more than one interesting thing happening in that molecule. But what we're focusing on is not the R there. So esters, I get my esters and ethers mixed up. Okay, ethers, E-T-H, ethers. Oh yeah, now I remember. Ethers have like the oxygen embedded. So I'm going to go R-O-R prime. That's my ether. Where R and R prime are not the same. Okay? And aldehyde, it actually has, I get my aldehydes and ketones mixed up. Aldehyde has a terminal, the carbon's terminal. So I have carbon, hydrogen, and then that carbon actually has a double bond oxygen, and then I have my R over here. So that's aldehyde. And I'll switch to blue for my ketone. See how, if you think this is similar to ketone. The difference between aldehyde and ketone is ketone has the carbon, double bond oxygen, and it's not on the exterior. So I'll put an R prime there and an R here. So that's the difference between the two. Esters. Oh, okay. So esters, I'll do red for esters, look like this. It has kind of embedded in it is kind of a carboxylic acid a little bit. So esters go like this. It's not in the middle, again, so I'm going to put an R prime and an R here. Oops, is that what I want to do? No, that's not what I want to do. Sorry. The carbon is singly bonded to an oxygen, and then we have R prime over here. That carbon is double bonded to an oxygen, and we have R over here. They look complicated, don't they? So that's your esters. But do you see where it's kind of like a carboxylic acid, but yeah, instead of R prime being an H, it's a... So, but can you see where these don't hydrogen bond with themselves because there's no OH? All right, now I have some examples. So these are all things that can hydrogen bond with themselves. So here we have ethyl meaning 2, okay, prop meaning 3, meth meaning 1. So we have ethyl alcohol. Here we have phenol. It's a type of, what did we say it was? Yeah, phenol. It's a type of phenol. Okay. Here we have the ethylene glycol. So eth meaning 2, and I don't know if this is, I don't know. I kind of fallen apart there. But this actually has 2 hydroxyl groups on either end. Okay. And down here we have an example of a carboxylic acid. This is a carboxylic acid. Carboxylic acid. Okay. And it's the one that has the hydroxyl group on the end. And sometimes, like this has 2 carbons, how did they get acetic acid out of it? I don't know, quite frankly. Okay, so those can all hydrogen bond because of the OH group. And these can't hydrogen bond. So we have the aldehyde up here. Remember, aldehyde has a carbon on a terminal, excuse me, the double bond on a carbon that's terminal. So this is an aldehyde. And then next to it we have a ketone, acetone actually. And then down here we have an ether. We have your little, you can tell it's an ether because of that. And then down here we have an ester. Make sure to find my ester. That looks like ester to me. Okay, so basically your R and your R prime are just methyl groups. So yeah, it goes back to Olivia said, do you need to be able to name these? No, you don't. But what you do need to do is if I give them to you on a test, can you recognize that these can't hydrogen bond with themselves?
What was the group for the bottom corner one you said?
Which one?
The diethyl.
The diethyl.
Oh,
It's an ether, yeah. And the thing that gives it away is kind of, it has this oxygen hiding kind of in the carbon chain.
Okay.
And your R groups in this case are the same R and R prime, but it wouldn't have to be.
So will we be asked to be like, look at acetone and say, oh, that's a ketone?
No.
Or just to ask, can a hydrogen bond or can it?
Yes.
Okay.
Yep. Look at acetone and say, can it hydrogen bond or not? And it cannot. Right. It can't hydrogen bond, but it has kind of, the oxygen is kind of a higher electronegative than the carbon, so you do kind of have a partially negative region over there. Okay. So it can't hydrogen bind with itself. And did we talk about this with mixtures? But if I back up a water molecule, so let me go ahead and I make my oxygen, my hydrogen, so that's my water, and I'm trying to dissolve acetone in water. So this is partially negative, partially positive, okay? And then this over here is partially negative, okay? Here we go, dot, dot, dot. Okay, that green dot, dot, dot there is a, it's just a simple dipole intermolecular bond because acetone's polar. Okay, then on here we have amines. Yep, but we need to, I'm going to just briefly kind of talk you through the different types of amines. There's the primary, secondary, and tertiary amines. This just says you have a nitrogen that has 3 R's. So this one simply says amine is this. You have R1, R2, whoops, or you want to call them single bond, single prime, double prime. Sorry. Oops. R prime, R double prime. How's that? Kind of stay consistent. Now, nitrogen is reaching out 3 times. Oh, see, check this out. Its group number is 5, so 8 minus 5 is 3. So you expect it to reach out. Now, in Lewis structures, we've drawn it with like dot, dot, okay? Lone pair electrons if it's all singly bonded. All right, so amines, actually, they come in flavors, primary, secondary, and tertiary. Primary means that 2 of those R's, is this right? Yeah. 2 of those R's are hydrogens. So if this is a hydrogen and if this is a hydrogen, okay, we basically have 2 hydrogens and an R group. So the first one is an example of a primary amine. This is a primary amine. We have nitrogen, hydrogen, hydrogen, and then we have this R group. Our R group is basically CH3, CH2. A secondary amine now takes it up a notch, so it gets a little more complicated each time. The secondary amine, now you just have 1 hydrogen around that nitrogen. So in a secondary amine, you just have 1 hydrogen. So that's the example here. Notice we have 1 hydrogen. Okay, what makes it secondary, I guess, is the number of non-hydrogen groups. There's where the 2 in secondary comes. Okay. So we have, again, our R's are the same. They're methyl groups, which they wouldn't have to be. The third one, for tertiary amine, basically you have no hydrogen. You have group, group, group. And this kind of goes back to what Mike said. You know, are R's just like hydrocarbons? Not necessarily. Okay, but we're kind of focusing on what makes it an amine is the nitrogen. Okay, that's bonded to 3 different R groups. So this slide then emphasizes, you guys would tell me OH, hydrogen bond, NH, hydrogen bond. What's the third one?
FH.
Yes, FH. In all of these cases, I could put, a partially positive up here and a partially negative over the oxygen, nitrogen, and fluorine. My point here is that here you can hydrogen bond, okay? Here you can hydrogen bond, okay? But down here, you can't hydrogen bond with the tertiary amine. And I think this works. I have a slide coming up that's saying the more alcohol groups you have, the more hydroxyl groups you have, the more likely you are to get the hydrogen bonding. So does this make sense that if you can have, let me draw my red, okay? This guy is, you can hydrogen bond 2 times. This guy, you can hydrogen bond 1 time. And this guy, you can hydrogen bond 0 times. Does that make sense? So the number of kind of regions that you make is kind of a player. Cool. So the boiling points of alcohols. Okay. So our alcohol was R-OH. Alcohols will have much higher boiling point than alkanes of similar molecular weight. Why is that?
Stronger bonds.
What?
Stronger bonds.
Stronger bonds, yeah. You can get hydrogen bonding with the alcohol. You cannot get hydrogen bonding with an alkane. Stronger bonds, exactly. Alcohols will have higher boiling point than their isomeric ethers. Now, find an ether. If you're like, I don't remember what that is, and you won't have to for the test, but an ether here is where you have an oxygen. You have an oxygen, but it's embedded in your carbon chain. An isomeric just means that you have the same atoms, they're just arranged differently. So we can hydrogen bond. Can you hydrogen bond with an ether? No, exactly. Okay, now this says, and this is something that we kind of talked about before, if this is my hydroxyl group, this is my OH, carbon, carbon, the more carbons I add, what this is saying is the boiling points increase. Why do the boiling points increase? What sort of intermolecular bond is kicking in?
Induced dipole?
Yes, induced dipole. Yep, induced dipole, exactly. Very good. branching. Oh, we talked about branching before. That's where I kind of butchered. So branching. So remember what branching is basically instead of having a hot dog, okay, basically you take those carbons and kind of move them in and kind of have them branching off of, okay. Does that, why does that lower the boiling point?
Makes it bigger.
Makes it bigger? What do you mean by bigger?
Spaces it out more.
This makes it spaced out more,
Wow.
I think. I don't know. This makes it spaced out, and this makes it like a ball. Yeah, and this makes it, and so this is, why is it, what intermolecular force is it that is less likely to occur here? It's harder to get, to isolate, to have your, it's not polar, it's harder to induce a dipole if it's a ball versus if it's a hot dog. You're like, oh, well, if it's stretched out, I'm going to make that partially positive, that partially negative. That's
Okay,
easy.
So the branching reduces surface area. Surface area.
Right, yes. Surface areas confuses me too, but yes. Yeah, it balls it up. It reduces surface area. Exactly. Yep. Versus stretched out. A lot of things hurt my brain anymore. It's an age thing. Okay. Like what? Okay, so we've been calling alcohols have a hydroxyl group. Diols have 2 hydroxyl groups. No, it didn't make it to my list. Okay, triols. Okay. And there's a lot of, and I'm not, is this right? Like with fats and sugars, and there's a lot of biomolecules out there that we consume that actually, if you look at the carbon chain, you're going to see these little hydroxyl groups. So boiling point increases. Why does it increase if you add hydroxyl groups, more hydroxyl groups? You're increasing more hydrogen bond regions. Yep, exactly. All right. We talked about like dissolves like Monday. And so this is actually talking about solubility like dissolves like. So we're looking for polar dissolved, polar, nonpolar dissolved, nonpolar. So alcohols, which are polar, of 3 carbons or less, and so that you're talking about methyl, ethyl, or propyl alcohol, okay, are infinitely soluble in water. So is water polar or nonpolar? Water's polar, yep. So soluble, that must be polar too. Now this says if you go ahead and go beyond 3 carbons on your kind of alkane portion of your alcohol, you go to 4 carbons, then you start to have a little bit of polarity issue when you try to go ahead and dissolve it in water. Okay? And with 4 carbons, you can have these different configurations. Let's see if I can butch this. Okay? This would be our hot dog carbon. Straight chain. This is normal propanol. We could go ahead and take 4 carbons, and the tert that it's talking about looks like this. Yeah, does that look right? 4 carbons. Okay. So this is tert butanol. And this is N-butanol. Cool. So we talked about stretching out or balled up. So this is more branching, right? And with branching, does it make it, sorry, there's my hydroxyl group. So with branching, which one's easier to induce a dipole on? Mike? Which one could get a region of negativeness and positiveness?
The right one
Why?
is the branching.
The branching makes it easier to put like a region of negativeness and positiveness?
Yeah.
But you said that this has more surface area, right? This one has more surface
Yeah.
area, okay? With
So
more,
that needs to be further apart so that it would be the one on the left.
right. So this one is easier to induce a dipole, so easier. And if you can induce a dipole, then you can go ahead and make it polar. Yeah. Whereas if you're adding carbon and hydrogens, you're kind of fighting the whole polarity thing. So that's why this one is soluble. It's still called soluble. And this one is only, what's it say? This one is infinitely soluble. Hang on. That didn't work right. Hang on.
Sounds right.
As the number of carbons in alcohol increases above 4, the solubility in water decreases. So this would be is infinitely soluble tert of the 4 butyl alcohols. Tert is kind of branching. I think I just proved my wrong one. Here, let's see if this, I'll have to think about that. But thanks for playing along with me. Let's see if this sheds any light. So I've kind of grouped these together, the first 4 together. You have a carbon, either it's bonded to 4 hydrogens, that's methane, or your carbon is bonded to 3 hydrogens and a chlorine, that's chloromethane, or you have, instead of a hydrogen, you have a hydroxyl group, which makes an alcohol, so that's methanol. The last column says, can you dissolve it in water? Okay, water's very polar, okay. Methanol, very polar. Chloromethane, a little polar. But methane itself, nonpolar. So you see that it doesn't dissolve in water. Well, it dissolves in water, but not in an infinite amount. And this actually is a good point. Remember you asked, how do you describe solubility? Well, right here, neck and neck, in the case of chloromethane or methylene chloride, we're describing it in grams of methylene chloride per 100 milliliters of water, and the other one is milliliters of the gas methane in 100 grams of water. So solubility, it just depends. So there's those 4. Okay, now these emphasize 2 carbons. Kind of again, we have ethanol, that's infinitely soluble. And up to 3 carbons, propanol, it's infinitely soluble. Okay. But propane doesn't have a hydroxyl group to hydrogen bond, making it polar. So propane's nonpolar, so it's only soluble to a certain degree. Well, this isn't going to explain this, but this actually, all these last 2 do is take our normal alcohols and bump it up from 4 carbons to 5 carbons, butanol and pentanol. But I guess this is a good point where, this lost me over here, but this where we add more carbons, it makes it less polar, basically adds a nonpolar end to it, and again, it's like dissolves like, so it's less soluble in water.
Can I ask a question? Could the difference between those 2 up there be that they're talking about the methyl, ethyl, and N-propyl and isopropyl in the first one, but in the second one they're talking about butyl?
Yeah, it could be. I'm going to take a look at that.
Okay, I was
Take
just
a running
curious.
start for it on Friday.
Sorry.
No, I agree. I agree. What else do we have? There's methanol. The phobic means fear, philic means love, so hydro means water. So hydrophobic means fear of water. So anything that's kind of nonpolar has a kind of fearing water sort of end. So I know it's kind of weird to look at, but this is the middle thing. This is carbon, hydrogen, hydrogen. Kind of see that? That's the green part. And then the red part is your oxygen, hydrogen. So it loves water, and the green part hates water. So this is going from 1 carbon to 5 carbons. So let me kind of make sure we're all on the same page here. So this is my carbon, this is my oxygen, hydrogen. I just think this is weird how your author's done this. Carbon, 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 okay? And then we have the hydrogens here, and this is your OH, okay? So the point here is we have the nonpolar part, and we have the polar part. And the one that has more nonpolar part is this guy. So that's why it's less soluble in water, like we saw on the previous slide. So this is showing you a mixture of water and methanol. See if you can, there's water. Okay. And there's water in methanol. So you can kind of see the CH3OH right here, the thing with the black. So we have the carbon, the 3 hydrogens, and this is your hydroxyl group right here. So it's kind of fun. Do you see how the hydroxyl groups of the alcohol are kind of bonding with the water molecules? It's kind of neat. Oh. Okay. Polyhydroxyl alcohols. So hydroxyl is an OH, alcohol is an OH. The more OHs you add, the more soluble they become. Okay. So carboxylic acid, we have an R group over here. At the end of the carbon chain, we have an OH and double bond, an OH and a double bond oxygen. So carboxylic acids will have relatively high boiling point temperatures compared to the regular, figure alcohol is just an OH, and a ketone is just a double bond O. Okay, so they have both of them. We'll be talking more about melting point temperatures and intermolecular bonds coming up. Are carboxylic acids soluble? It depends on how long is your R group. Okay, so if your R group gets too long, usually they're soluble. Carboxylic acids are soluble in water, but if you go at 10 or above, it's like insoluble in water because you basically are adding on that alkane portion. Remember, aldehydes and ketones both have that carbon double bond oxygen, but an aldehyde has the carbon singly bonded to a hydrogen, and the ketone, that double bond oxygen is bedded in the carbon chain. Then we go back to amines. I looked at my slide, and I think we talked about this. Okay, we talked about the primary. For primary, we do like a 1 with a little circle. This is my primary amine because it only is connected to one thing that's not a hydrogen. This is my secondary amine. We got 2 things that aren't hydrogens. This is my tertiary amine. We have 3 things that aren't hydrogens. And with tertiary amines, you don't have any hydrogen bonding. So that kind of explains their solubility and their boiling point temperatures. Oh, and this was a little note. This is no kidding. This is true. So I was getting ready for today's lecture at home last night, and this is a slide I had a year ago. So a year ago, I was right at the same spot. So anyway, I know. So don't forget your lab write-ups are due tomorrow. And remember, and we're going to start with tomorrow, that I just generally have office hours if you come by, if you have any questions before lab, and even then after lab. So if you have questions about your lab reports, that might be time. You can talk with yourself amongst yourselves or talk with me about your questions about your lab reports. Okay? All right.